So if I were to ask you, what was the hottest thing in the universe, what would you pick? I know. You'd pick me, right? No, I understand. I get that a lot.
Cut.
What?
Done. We've talked about this.
If we want to talk about hot things, perhaps the best place to start is with the familiar. Perhaps the first thing you thought of was fire, which is, without a doubt, hot. However, an ordinary fire, which has a temperature of 1 or 2,000 degrees Fahrenheit, isn't even competitive in a hot contest. So what's hotter than a familiar fire? Well, there's the blowtorch, which is about twice as hot as a campfire. But even a torch isn't competitive in a contest for the hottest thing in the universe. For instance, the surface of the sun is twice as hot as a typical torch, and the center of the sun is 3,000 times hotter than that, weighing in at 16 million degrees centigrade. And even that incredible temperature is eclipsed by the technologies employed by my colleagues and me to study the laws of nature. Using huge particle accelerators, we could smash beams of subatomic particles together at near the speed of light and generate temperatures 1,000,000 times hotter than the center of the sun. We particle physicists do have the coolest toys. Well, hottest, but you know what I mean. A really interesting thing to think about is what happens to ordinary matter when it encounters temperatures like these. To understand that, we can remember some familiar phenomena and then learn about some more exotic things that you might not have heard about before. To begin with, we know about the states of matter that we learned about in school, specifically solid, liquid, and gas. Of course, things are solid when they're cold, gaseous when they're hot, and liquid when they're in between. So how does temperature affect the structure of matter? To understand that, we need to think both molecularly and atomically. In solids, molecules are moving very slowly, slow enough that the forces between molecules are strong enough to hold them in place. In liquids, the molecules have much more energy, and the interactions between molecules remain, but dominate less. This leads to phenomena like viscosity. When matter is heated even more, the interaction between molecules becomes negligible, and matter turns into a gas, with molecules bouncing around randomly. So, until now, I've described things that you learned about in school. But it turns out that there are states of matter beyond the familiar three. So what happens if we take a gas and turn the heat up even more? To understand this, we can zoom in on a single molecule and see what happens. At a certain temperature, the energy is enough to rip molecules apart into their constituent atoms. If one raises the temperature even more, the nucleus of an atom can no longer hold on to the electrons, and the result is that you have electrons running around willy-nilly, unbound to an atom. The nuclei might initially hold on to some of its electrons, but eventually the temperature will be so high that what you have are electrons and bare atomic nuclei running around. The temperature at which these stages occur depends on the molecules and atoms under consideration, but what I've described here is generally true of all matter. When matter is heated enough that the electrons are being pulled off the atoms, this is a new state of matter called a plasma. You've seen plasma in fluorescent light bulbs, lightning bolts, and in those cool plasma balls. The temperature of the plasma in lightning bolts can be 10 times higher than what occurs in a blowtorch. Creating an entirely different new state of matter is pretty amazing, but we're not done. Let's raise the temperature even more. To see what happens then, we need to turn our attention to the atomic nucleus. As the temperature increases, the nuclei have so much energy they can no longer reliably hold the protons and neutrons together. But even that amazing achievement isn't the final word. In order to simplify the language, we use the word nucleon to describe both protons and neutrons. This is because they're both inside the nucleus of an atom. Nucleons are each made of 3 particles called quarks, and the quarks are held very strongly indeed. In fact, under ordinary conditions, one cannot pull a quark out of a nucleon. However, the temperatures we can achieve in particle accelerators are anything but ordinary. If we heat matter enough, we can literally melt the nucleons and have the quarks and a particle of force called the gluon run around no longer bound together.
Okay, so at this stage, what happens if we view this as density in of itself? Okay? If you were underwater and your whole world was underwater, And one day you went in to an area, like a cave, and you could heat that cave up to a point that basically within that cave you would have evaporated the water. And so then you would be acting out in a completely different density within those parameters. And so then physics and everything else would be viewed differently because you've affected the density rate.
This outrageous state of affairs is a
And so basically, all of time space, if you view that as that we view time space, it's a range of density. Now, there's ways of going past that.
new form of matter called a quark-gluon plasma. I'll say that again. A quark-gluon plasma occurs when the temperature is so high that individual protons and neutrons literally melt. So you may be wondering if a quark-gluon plasma is a real thing or just an idea. It turns out that scientists can create quark-gluon plasmas at specialized particle accelerators. At the Relativistic Heavy Ion Collider on Long Island, also called RHIC, and the Large Hadron Collider in Europe, also called the LHC, physicists shoot bare atomic nuclei at one another like shooting two bullets together. The temperature in these impacts was last common in the universe a millionth of a second after the Big Bang. We see here a simulation of the collision at the LHC in which two nuclei of lead are slammed together and a quark-gluon plasma is formed. Physicists
And now think if for one brief moment you have fully changed, basically, the density, aka how time-space is acting out, briefly.
generate collisions like these about 1 month each year. The study of quark-gluon plasma is still a relatively new science, but scientists at RHIC and the LHC are studying their data, and it is guaranteed that the next few years will teach us something very interesting about this hottest state of matter.
Or view it as you have now briefly altered time-space, aka the density in which it reacts. Now, then expand that up and imagine that we are living in time-space, and so all you've done is recreate a condition that's like in a different dimension, like a different viscosity. And the easiest way for me to explain that would be if you imagine like water and air. And so if you're going around in water and your whole existence is in water, you don't really understand how things interact in the air or how they would be different. So, however, if you can figure out a way to go up there, you can do a lot of crazy stuff. And so what this is showing you is the blueprint of basically that dimension, that viscosity of time-space.
And that is totally cool.
Thank you. God bless. Bye.